So here I'm showing the very first property I was talking about before we move on to this larger size matrix. That we can look at this from this definition right here. We're going to look at the important properties. And so first we're going to denote the determinant like this, and we can look at this as a map of functions on three rows. The first row is a1, a2, a3. Second row is b1, b2, b3. Third row is c1, c2, c3. They're written like this. R1 is a1, a2, a3. R2 is the second row here. R3 is a third row there. So we can look at this as a function on that first and three rows. Or you can look at this as a columns. So V1 stands for the first column, A1, B1, C1. So that's a column vector and that's a row vector. And V2 is the second column here, that's a column vector. So we can look at this as a three variable function, a scalar valued functions. Let me say that again. So we can look at this determinant as a three variable scalar valued functions. The variables can be those rows of the matrix or columns of the matrix. So the following statements can be regarded as a columns or as rows. It doesn't matter. Both will, for both cases, the following statements will be valid. So here's the first statement is the following. We're looking at the determinant of the three variable scalar valued function. So here looking at the first variable, not touching the second and third variable. First variable is written as a linear combination of two vectors. So when we, like the partial derivative, if you remember what those are, if you have taken the Calc 3, we're not touching W2 and W3, we're only looking at the first variable slot and pull out a linear condition. So if you have a linear combination on the first, so we're looking as a kind of one variable scalar valued function, it has a property that a times the function value of the W11 in it plus b times the function value of the W12 in it. So if you ignore W2 and W3, because this is not changing, if you just focus on the first entries, this is exactly the linear condition, linear transformation. So again, it doesn't matter if these W's are rows and a column, but it has to be all rows and all columns. And it actually doesn't matter if you're doing this with the W2, so you can split this W2 or decompose the W2 as a linear combination of something, and not touching W1 or W3, you can kind of split in this way. So one at a time, not all three things at the same time. So you can look at the first entries and do this one. And now we have several entries here. For each of the entries, if you can split these entries into a linear combination, and then you can keep repeating this. So we'll see the algebra that's coming out of this. So let's think about why this is true. Because the way we define it here, and it is just a 3 by 3, and D1 and D2 and D3 are the determinants of 2 by 2 matrix, so we know how it looks like. The sum of the products of two elements, they're all coming from rows and a column individually. So if this first entry was a row, then we're actually rewriting A1, A2, A3 as a linear combination of different numbers, not vectors. So A1, A2, A3 is replaced by this type of numbers, components of these vectors. So from there, by looking at this structure, you see how this D1, D2, D3 distributes. It's kind of obvious that why this linearity follows when we look at this first entry as a row. If you look at this first entry as a column, then we're actually splitting A1 and B1 and C1, and A1 is split into two parts. If you look at this as a column split into linear combination of two things, and this one here is written as a linear combination of two things. So A1 is splitted for that part. The linearity is clear. And the key part is that D1 does not have anything in the B1 and C1 in there. Remember, D1 was a matrix consists of the second and third entries here, columns. So it's not going to split anything. Only thing that splits here inside the D2 and inside D3 and A2, A3 is untouched. So linearity kicks out in here, and no more complicated splitting is happening as we replace this one here, first column, with a linear combination of two vectors. Only D2 and D3 is in here that involves B1 and C1, because D2 is a matrix with the B1, B3, and C1, C3. So it deserves some writing, and the proofs are written down carefully. So, but I think is not hard to believe that this form right here, because they're kind of isolating each other index-wise, this type of linearity follows fairly immediately from this shape of the definition of the determinant. Now let me introduce the second part of the theorem, which is the following. So determinant of VWW, when this any of these two columns are equal to each other, then the determinant is going to be 0. If the first two columns are equal to each other, it's going to be 0. For one, the first and the third is equal to each other, it's going to be 0. And this result is valid for the rows as well. But the proof we're going to give here is only for the column cases. And later on, and we're going to extend this result to the rows, but the proof we're giving is only valid for columns here. Okay? So let's look at this part and understand why this is so. For example, if the third column here and the third column here and the second column is equal to each other, and this entire determinant is going to be 0. Because of the following. For example, if you look at A1 and D1 here, D1 is this 2 by 2 matrix. Now we're looking at the 2 by 2 matrix where the two columns are equal to each other. So if we do this inductively, and this 2 by 2 case will be the base case, which is easy to check. If there's any two columns equal to each other, determinant will be 0, cross multiplying is 0. You can stop the video and easily verify. Suppose we're doing this to a lot bigger size, then we're dealing with smaller size of the matrix. Therefore, inductively, we have that result. So we took care of the D1 by induction. Now let's look at D2 and D3. Now we're looking at these two columns that are equal to each other. D2 will be the first and the third column, and D3 will be the let me say that again. D2 will be the first and third column, that's right. D3 will be the first and the second column. So first and the third column and first and the second column. They are exactly the same because the second and third columns are equal to each other. So D2 and D3 are equal to each other. What about A2 and A3? A2 and A3 are second and third column, so they are equal to each other. So these two cancel each other because A2 and A3 are equal to each other. And the 2 by 2 matrices, determinants of those 2 by 2 matrices, D2 and D3, are equal to each other. Okay, let's see if that's going to hold like this for the bigger size of the matrix. If I have a long size of the rows here and bigger size of the matrices here. It turns out a lot of this term is going to be exactly 0. Only two terms survives. Suppose there is these two rows, two columns are the same, and everything else here, we don't have any condition on it. Whenever we choose A1, then there will be these two columns happen to be the two columns of some smaller size matrix. And then if we look at other terms, A4 and A5, there will be always these two rows. They're equal to each other. By induction, they're going to be all zeros. Only thing that it makes a difference, non-zero, is when we choose this A2, then we eliminate this one. We no longer have these two rows equal to each other. When we choose A3, because we're eliminating this one of the same rows, we don't have this non-zero, but the same argument goes here, that it turns out easily by deleting these two columns which are equal to each other, you get D2 and D3 exactly equal to each other, however this big this matrix is. So I think it's fairly easy to see and easy to explain, especially in words, why these two columns equal to each other has to be 0. I hope that was fun. Now next part is actually a very important part. This is important too. Next part is if you combine these two results, 1 and 2, we easily get this result. So it says if you have V and W, and if they swapped each other like this, then what happened to the value of the determinant is change its sign. If it is Wx and swapped, then it's going to change the sign again. So this is an interesting property. This property is called the skew symmetric property of the determinant map. Now this one's more algebraic, so I'm going to show the proof here. Let me explain the first line, W. Okay, so we know that if you look at the right hand side and V plus W, because W and X is fixed and this is the only kind of splitting part, so it's going to split to determinant of VWX plus determinant of WWX. We've seen that WWX is going to be 0 because W repeated. So it doesn't matter as long as you put, if you put any redundant column inserted here, if it is a W or X or W plus X, whatever, it's not going to change the determinant value. So it's the same as VWX. That was the property that we showed earlier. Same thing here. If you play with this W and V, okay, we're comparing VW and W and V. Think about it here. V is the second slide, so if I insert this V here, this value is not going to change because linearity, using linearity, we split this determinant of WVX plus W, the determinant VVX. VVX is 0, so that's the same as WVX part. So this and that is written in a slightly different way, but it turns out this V plus W and W plus V, that's the same. So these two things are the same, that two things are the same. So if you add this together, we can do something. So here's what happened. Left hand side and right hand side added together, and what happened to these two right hand sides here is that W plus V plus W and W plus V is the same, X and X is the same. So this V plus W written here and X written there, and if you add these two W plus V, that's a linearity in one column there. So this is true. So the left hand side is, we have everything we wanted, and right hand side turns out to be 0 because we have now V plus W and W plus V repeated. So it's 0 again. So because it's 0, then you can see V plus W and W plus W and V and W, so they must be opposite sign, so that they add up to 0. So that was the proof of this skew symmetric property, and from these two properties, that was kind of fairly easily deduced from just to have this shape of the determinant, definition of the determinant. Now I kept saying the definition of a determinant of a larger size. Now finally I'm showing that and how it looks like. If you have 4 by 4 determinant, then we're going to write down these top row entry A1, A2, A3, and A4, like I said, is like alternating its sign. Then the determinant D1 would be this 3 by 3 determinant right here, and D2 would be 3 by 3, removing the second column, and this, B1, C1, D1, and B3, C3, D3, and this row columns. D3 will be the 3 by 3 removed by removing the third column, and so on. So that is the definition of the determinant of 4 by 4. I think that gives you a very clear idea of how this larger size, for the larger size, how the determinant is defined. But for all those, because of this simple shape here, we have these three properties, and that's fairly easy to prove, like I said. Now I introduce this skew symmetric property on the columns of a matrix and the determinant, and this is a very important property, and we're going to use it to understand a little bit more about the definition of the determinant map. Okay. So here's the determinant of 3 by 3 again. So I've already introduced this notation, determinant of first column and second column and third column separated, look at this determinant as a scalar valued function of a 3-variable, where the variables are column vectors. Now this is, I don't know, this is my invention of this notation. It's very, very useful to understand what this is. It's just like a dot product, if you know what those are. But instead of dot product, we have this different symbol, star product, let's say, or determinant product. I don't know how to name this one. But instead of using this determinant, v1 comma v2 comma v3, we're going to use this notation, v1 star, v2 star, and v3. Altogether, this will be a scalar, a number, just like a dot product. But it is slightly more complicated than dot product. The way the algebra works is it's similar, and just a few more things in it. So here it is, the multilinearity. If I have a dot product of two things, we don't usually consider that. You can't consider dot product of three things. Only the comparison is this multilinearity. If you have a dot product of v1 dot v2 and you don't have this vector, then this multilinearity is true. This dot product works just like a product of numbers, so you distribute things. So it works just like that. So if I have v1 and w1 in that first slot, and then star multiplied by like this of the vectors, this whole thing is going to be scalar. But that's the same as, v1, v2, v2, v3 multiplied to v1 like that, plus v2, v3 multiplied to w1 like that. If these were a number, this is called a distribution law. Only thing we have to be careful here is you have to keep the position v2, v3 to the right, and then whenever you want to change this order, you have to deal with the skew symmetric property. Now let's look at this slightly more complicated situation, that the first slot is replaced by sum of two vectors, and second slot here is replaced by sum of two vectors, and so on. So this is still three vectors multiplied together under this determinant law, map, and become a scalar. How it's going to expand is usual expansion, just like a number. Just make sure when you multiply, you keep the order the way it's multiplied from the left or right. So, when we distribute this one, we're going to multiply v1 to v2 and v3, or you can start it from v1, decide to go to w2, and then w3. All sorts of combination. You're not going to multiply v1 to w1, but you can multiply v1 to any of these two terms, then any of these two terms. So if you think about it, this is 2 times 2 times 2, so there's supposed to be 8 terms for a lot. Okay? We're not going to write down all the 8 terms, but I'm going to show you some of the terms and give you an idea, right? Consistent way of expanding this one. So first I'm going to start with the lowest index, v1 multiplied to v2 multiplied to v3. Okay? So that's the one term you will get. Then I'm going to keep the v1 as much as I can. I already multiplied v2, so next choice I had is a v1 and w2. Then I can still do v3. Excuse me, I was wrong. v1 and v2, and then I have a choice of w3. That's the way I went. So v1, v2, and I already did v3, so I left with the w3. That's what I wrote here. Okay, so v1 and v2, I did v3, v1 and v2, I did w3, so there's nothing left. So I will go to next choice, v1, not v2, but w2. Then choose the first one, w3, and here v1 and w2 and v3. That's going to fall out. Let's look at one more term, and v1 and w2, I already did v3, so v1, w2, and w3. So that will be here. So by doing that, you will already have 4 terms, the 4 more terms coming out. So that's so each individual terms here is a scalar. So if you add those 8 numbers, the same as doing this one. So a little bit of multilinear algebra, which is basically just multiplying out a bunch of sum of numbers. Same pattern. Alright, here's an interesting lemma. Skew symmetric property. So we see this v1 and v2 and v3 and all those things. It's just an arbitrary choice of 6 vectors. But suppose you have v1 star v2 star v3. If you go back to this determinant map there, that means this v2 and second column and third columns equal to each other, you know that's a 0. We've seen that before, right? So that's going to be 0. What about this E2, E2, E3? Whatever any two vectors equal to each other, this star multiplication will disappear to 0. Or if you swap it, it changes the sign. So skew symmetric property implies that, and you can also show that. Okay, so I hope you got used to this star multiplication a little bit. So this is a fundamental case. E1 is a standard notation for the column vector 1, 0, 0. E2 is a 0, 1, 0. E3 is a 0, 0, 1. So if you follow the definition, because there are lots of zeros and a few ones, it's not hard to show that this one has to be 1. So this is a fundamental case. So if you do E1 star E2 star E3, the determinant map, it's going to be 1. Now let me show you how this fundamental case can be used to kind of rewrite the determinant of this one. So here's again, this is the 3 by 3 matrix, and the determinant is written by this first vector star multiplication, second column vector star multiplication, and third column vector. So when we look at this column vector, we can write this one. It's a linear combination of E1 and E2 and E3. So A11 is our first entry, so we multiply to E1 and 0, 0 in there. So if you look at this E2, if you multiply A21, A31, E3, if you combine this one into a component, you get exactly this. So that's one way to write it. And the second column vector has this different coefficient, but it's made out of the same vector, E1, E2, E3, same basis, E1 and E2 and E3. Now, like we did, just combining all this thing, we're going to expand this on out. Now we have 3 terms here, and 3 terms here, and 3 terms. So 27 terms are supposed to fall out. The good news is that when you combine these bases, E1 and E2 and E2, those are all possibilities. Whenever there's E2, E2 repeat like this, it's going to be 0, right? E1, E2, E2, that's going to be 0. So we don't have to do that. Once you choose E1, and next time you decide to choose E2, then you don't have a choice. You're not going to choose any E2 and E1. You have to choose E3, so that is a non-zero term. Okay? So let's see what we have. Okay, I'm showing the first term. E1 and E2, E3, that's okay, right? And if I collect these coefficients as A1, 1, A2, 2, and A3, 3, none of these basis vectors equal to each other. That's good. Now let's look at the second one. I started still with E1. I already chose E2. I'm not going to choose this E1. I have to choose the remaining case. E3 is the only option I have. Okay, so E3, then I have to go back to E2 because E1 and E3 are selected, so I can't choose these, so that is going to be 0. So this is another case, E3 and E2. So I've collected this coefficient carefully. Let's see the next term. Now we're done with this E1 because these are the only option we have, and it kind of determines the third part. So let's start with E2. Then you can go to E1, then E2, E1, you don't have a choice. Now last one should be E3 so that it survives. So E2, E3, E1, and these are the coefficients. At this point, let me mention what is happening to this index. These columns, this you get second entry, second subscript in there, that is telling us that these are the columns. We're choosing something here, A21, A32, and A3, and this is the same, 1 and 2, 3. This second subscript is always columns. It never changes however you chose it. So that corresponds to this space and that space and that space. But the first subscript is changing, 1, 3, 2, and 2, 3, 1. They're exactly this order of a subscript for the basis member. Alright, let's do the next one. A2, you started from there. I think we already did A1, so we have to go to E3 and then E1. So 2, 1, 3 is what I did. Next one will be, so we're done with this 2. Okay, let's start with the 3. You can go 3, 1, and 2. So that's 3, 1, and 2. And the first subscript is 3, 1, and 2. Now 3, 1 we're done, so we have to do 3, 2, then you're left with just 1. So 3, 2, 1 is there, and 3, 2, 1. And that's it. That's all we can have. Other than that, all the other terms has 2 repeated columns, so it's going to be 0. That's some boring work, but it's not very interesting. So following this part is interesting to me. I think it's very interesting. So let's see what happens. Notice that all this thing here is E1, E2, E3, all multiplied here, E1, E2, E3, in a slightly different order. And we know what happened. We swapped these orders. It just changed the sign. One at a time, it changed the sign. So by swapping these vectors, you know we can change all of them to E1 star, E2 star, E3. And that's what we're going to do. So I want you to look at this vector here, E1, E3, E2. So we're going to take the 2 vectors and swap it. And if that's not enough, you keep doing that until we get this E1, E2, E3. Right. If I swap these 2, 3 and 2, we get E1, E2, E3 right there. So one swap will do. If you swap it one time, the negative will pop out, right? If you look at this one, okay, I'm going to swap these 2, then I will have 1 here and 3 there. If I swap this again, it's going to be 1, 2, and 3. So by swapping E1 2 times with the other one, we get back to, we have this E1, E2, E3. Right? But we swap it 2 times. So one time you get a negative, another time you got another negative multiplied, so it's a positive. Now if you look at this third one here, then I can only swap this 1 and 2 and that's it. So it's one swap will get you to the 1, 2, 3 order. So it gets negative. What about this one? I can swap 3 and 1 and 3 and 2. So that'll keep the order 1, 2, and 3 goes all the way to the end. Therefore, it requires 2 swap. So negative, negative, it's positive. So that's untouched. What about this one? 1, 2, so I'm going to swap 3 2 times to put 3 all in the back. Then we're going to keep the order of 1 and 2. That was a 2 swap. To change this order, is a third swap will change the 1, 2, and 3 there. Alright, so that's there's an odd number of flips, so it's going to get negative. Alright, so what's going to happen is all this thing will change to same scalar E1, E2, E3, which is 1. Then all this thing will have just a negative sign alternating in this order. Now we actually went through all the swapping, so let me explain locally. If you're looking at this term with these a's and multiplies and there's determinant in terms of this base member E1, E2, E3, how are we going to determine the sign here? Is there a way to just look at it here and determine? Of course. Let me just explain in the following way. Now first notice that this first entry subscript is lined up exactly the same as the order of this determinant part. So I extracted that entries, that's the important part, x, y, z. And what we were doing is that we were just reordering by swapping 2 numbers n times, for example. If that requires 3 times, n is going to be 3. Reswapping of 2 numbers. By doing that, we'll reorder this one as 1, 2, 3. So every time we do that, what we do here is we change the sign of this entire thing by multiplying -1. So if we're doing 3 times, that's going to be -1 raised to the 3rd power. If you're doing 2 times, it's going to be 2nd power. So this will be a nice multiplicative way of writing the sign change. So here's the bottom line. So if we have this x and y and z, and this part, you don't change this part, this x and y and z, we just keep this coefficient like this. What we're changing is the star multiplication. As we do that, only changes is the sign change. So after we're doing all that, we have E1, E2, E3 lined up nicely like this, and there's this n recorded, right? There, sign change. Okay, so that's how the individual terms going to change. It involves this information about swapping two numbers n times. Okay, so that's how you determine the sign of the term that fall out in the definition, or the definition of the determinant, using this symmetric linear algebra, skew symmetric algebra. But let's think about these possibilities, how many terms are there and stuff. Before, I was just multiplying 3 times 3 times 3 in 3 by 3 case, but you know there are a lot of zero terms. So what we end up at is that we are not repeating any of these first entries, because that will correspond to choosing E1 star E1 and something like this. It has to be 0. So we're not choosing any repeats of this x, y, z. So if you think about that, the possibility is that you can choose anything here in 3 things, and because you choose one of the out of 3, it leaves only the possibility of 2 remaining numbers and 1, so it's a possibility of 3 times 2 times 1. Then this is denoted as 3 factorial, like this. 3 times 2 times 2 times 1. If there's 4 by 4 matrix, then it'll be 4 times 3 times 2 times 1. Right now we have 6 terms, and if you go back, and there were actually 6 non-zero terms. So let's practice what we just did here. So if you're looking at this A3 and A22 and A13, okay, the second entries of the subscript is 1, 2, 3, so that's our requirement. Another thing is a 3 and 2 and 1, right? So this must have come from E3 star, E2 star, and E1 star. But we reorder those, not this one, we reorder those, and then it's going to change the sign. So if you look at here, how many flip is required, that was very last one. So first you can send 3 all the way to the back, that's 2 swap, and 2 and 1 swapped into the third swap, so that must be negative. It's like that. Okay, let's practice another one. If you're looking at it here, and multiply by E2, E3, E1, then it's going to be reordered, and that disappears because after you reorder it, E1, E2, E3 is 1. So we just have to determine the sign of this one. 2, 3 is in a good order, so if I move 1 here and 1 there, that requires 2 swap, and then it's going to be 1, 2, 3, so it's even. So even number of flip will get you eventually the sign positive. So this term with a positive sign will show up in that 6-term expansion of the determinant map. So there are more terms, but this is how you do it. You look at this index and think about how you swap these things so that you order it in 1, 2, 3. Well, let's practice with a little bigger size. This is a 4 by 4 case. So again, when we choose entries for each of the term, we're going to choose 4 entries from each column in a way that if you choose A21, you're not going to choose any of those rows, because once you choose 2, A21, and then your first entry is 2, and then you can see all these 2 appearing here, so you don't want to repeat that. So if you choose one element from the first column, and then you have to remove that A22 from your choices of the next entry, so that's 3 choices leaves us. And since we have chosen 2 elements, now that for the third column we only are left with the 2 choices, and finally have 1 choice left. So the number of terms we can combine in by doing that way is 4 times 3 times 2 times 1. 4 factorial, which is 24. So here's a sample, and I choose A41, A22, A33, A14. So these came from actually expanding that star multiplication. So it comes with this star product, E4, E2, E3, E1. But by rearranging those EIs, we can rewrite it as E1, E2, E3, E4, all star product. Then, by the fundamental lemma for this 4-dimensional case, the determinant of that ordered star multiplication is going to be 1. So that's just this term. But as we do that, is going to pick up the negative sign, even number and odd number that will determine the sign of this term. So 4, 2, 3, 1. 4, 2, 3, 1 is written here. So for example, 2 and 3 seems like already ordered. So I'm going to send this 4, for example, to all the way back by swapping 1 time, 2 times with 3, and 3 times with 1. So 3 times swapping 4 with all this thing will put the 4 in here at the end and 2, 3, 1 in front. That took 3 swaps, odd number of swaps. But 2, 3, 1 is here. All I have to do now is to move 1 to all the way to the front. So since 4 is gone, all I have to do is 1 swap with 3 and swap with 2. That's even number of swaps. So that doesn't change the parity. So earlier there was a 3 swap. So altogether is odd number of swaps. So negative 1 raised to that odd number will be a negative 1. So that's why it's going to pick up negative sign there. Very nice. So let me choose another term. I chose this one. So 3, 4, 1, 2. Then I need to swap this one. Okay. So let's see. 1 and 2 is in a nice shape. I'd like to put 3 right behind 2. So it's 1, 2, 3. It's in the good shape. So to do that, I have to swap with these 3 elements. So 3 is going to go there by swapping with the 3 element. So 3 swap, odd number. Now we have 4, 1, 2, 3. 3 is gone there. Then if I move that 4 all the way to the back, and that'll be it. So that's 1, 2, 3 swaps. So 3 swaps together makes even number of swaps. So that this one remains positive. So that's how you're going to determine the sign of all possible terms that fall out here. There are 24 terms, and by doing this process, you're going to put those in a position E1, E2, E3, E4 with some sign in front of it. Those are multilinear property and then skew symmetric property on its own right, and it is very, very important properties for the determinant map. But that the connection is very, very important for the following statement as well. And some advanced textbook actually introduce the determinants in this way that it's presented here using the swap and idea. But we're going to use the multilinearity and skew symmetric property to understand this definition, right? We already did that with the 2 examples, so this is some general statement. So here's you're looking at this notation of n by n matrix with this entry denoted by aij. I is the rows and j is the column index. Now we're looking at the shape. This n entries are multiplied to each other. So all the second entries, second index here is 1, 2, 3 all the way to n, just like we did it. So we're picking an element from the first column, element from the second column, and so on, all the way up to element of the nth column. We multiplied each other. Product, take the product. First index here, it's varying. It's a sum choice and different choice. In a way, if I made this choice, like let's say there was 11, then 11 will never appear again in this first entry or first index, because that will correspond to multiplying ek to ek. Okay, then that's, ek star ek is a 0, so you don't want to repeat that. If you were listing down the numbers in a way that never repeats, number through 1 through n, that's what's supposed to happen here. That is called a permutation. So this Sn here denotes all collection of all permutation of n numbers, how you list them down in order. So these there are number of elements in that Sn is n factorial, like we have seen 4 factorials and 3 factorials. This notation here is called the sign of that permutation. So if it takes even number of swap to get this first indices in correct order 1, 2, 3, 4 all the way up to n, if that took even number of swap, then this sign will be negative positive 1. If it took odd number, it's a negative 1. It's kind of strange that it's not quite simple. It's not that simple to explain why it doesn't change the parity. For example, if I have certain, let's say A3, 4, 2, then if someone tried to swap this, put it into order 1, 2, 3, 4, let's say that took 5 swaps, and different person did that, and then it took, let's say, 11 swap. And this definition tells us that the number of swaps required to do that must have the same parity. You cannot have one person took 5 times and the other person took 12 times. That makes no sense with this definition. So if you just look at that statement that I just said separately, it's not that trivial. It's absolutely a non-trivial statement. But if you look at this statement right here, definitely according to our definition, and there must be this sign, because it's this general polynomial identity, that sign must be fixed. It's not going to change. So you can actually use this as a proof that sign of the permutation is well defined. Doesn't matter who does the swap, and it's going to be always even or odd. It doesn't change from even or odd by different person or different attempt. So it's already interesting statement, but here it's very symmetric definition. We're not picking out first row or any special treatment to any part of the determinant. Everything is kind of well treated here, and mathematical term is called symmetric. Well, I feel like I already gave the proof of this statement by looking at 1, 2 degree, the size 3 and size 4 cases. I will leave that general detail to you, but that should be it. Alright, let me emphasize it again. This is very, very important statement about the determinant, but we're going to mainly use this one to prove the following, which is this statement here. So I abbreviated notation sigma 1 and sigma 2 like this with a subscript, so that there's not too many parentheses around. So this is exact copy of what you see in this permutation definition. But what you see in the right hand side here is that these two indices are swapped. One appears first and sigma appears later. And if you look at the last one, n appears first there and sigma n appears later. So because these came from the indices of these entries, these two correspond to the term of a determinant of this Aij, and this corresponds to actually the determinant of this matrix transposed. And this one says if these individual terms have the same sign, and if we're looking at the transpose, there's absolutely one-to-one correspondence from this term and then transpose the term. Okay? So when we do that, we have a one-to-one correspondence in between the terms, but the sign change is unclear. So this one connects that. Okay, if you're looking at a matrix Aij, then its transpose is going to be Aj, diagonal term, of the diagonal terms. They're swapped to each other. When we do that, if the sign doesn't change, then that's a proof that the determinant actually doesn't change. So determinant of the matrix is equal to the determinant of its transpose of a matrix. It's the same. And in the proof of that, we'll use this one. If you swap these two entries, the sign doesn't change. Okay. Alright, I wrote this statement up here again, so it says toward the transpose. So we're going to use this result to connect to the statement that determinant doesn't change when you take the transpose action. Alright, proof is really fun and it's easy to explain, but it requires a clever idea of organizing information, so I'm presenting the proof here. First, I wrote the first indices in here in the top row, Okay, so that comes from the row. That's why I call it index row and index column index. So 1, 2, 3, that's the column index is written down there. So, okay, that's the first part. Second part is this indices, explaining the idea of the transpose. So that row becomes the column index, then the column index becomes row index, and that's why it showed up here. Now think about that, the relationship between these two indices is described by this, right? Swapping these two rows when we organize those indices in this way. Now, this result is about the sign. So what we're going to look at is that when we do the swappings here, and it's going to be rearranged, keeping the rows and the columns in the same, kind of in the same row here, and see what happened to that part, and that'll pretty much it. That'll be it. So let's see. Let's do the M swapping. We're going to do the swap to rearrange this number sigma 1 to sigma n in an order that it says 1 through n up here, right? And then that's going to affect the bottom row because they go together, right? These are going together. I think I misspoke. This we're swapping these n numbers so that it lined up 1, 2, 3 through n is right, but we're actually making this one and pairing this up so that we can kind of trace them down. So there's no reason that these should go together. It's just indices written here, and we're about to swap, and tagging these each number with this 1 through n is kind of helpful, right? That's the right way to say that. So we have these sigma 1 through sigma n. We're doing m swapping to reorder, and then we tag this one with this additional number so that we can kind of track them down. So I wrote it like this. These sigma 1 through sigma n is written up here. Now it rearranged, and if we do that together with that n, if we do the same action to the 1 through n, it's going to be rearranged. So I'm going to rewrite it as a tau 1 through a tau n. So let me remind you of the following. This is exactly how we define the sign of a permutation. If you have this number, the first entries lined up like this, and if you do m swapping, and then we rearrange this number 1 through n, if it took m swapping, and the sign will be -1 raised to the mth power. Okay, so we see with all the notation, we have kind of named everything. But if you look at this one, it's not quite arranged the way we wanted. So for example, we wanted to write this term in this way so that the second entries are lined up as 1 through n, and second entry is supposed to line up 1 through n, but it's not like that. So first we have to rearrange it like that. So first we wrote the first index and the second index there, but we want to rearrange it such that there's a 1 through n down there, and whatever that corresponding thing up here there. So maybe we should really, in this part here, we're going to put this a1 sigma 1 to somewhere else, and a2 sigma 2 somewhere else. So reordering, it doesn't change the sign. This is not a star product. This is usually scalar product. So however you rewrite the product, it doesn't change its value or the sign. Then from there we're thinking about going back here again. So it's kind of reverse process, right? So that's why I'm using this diagram, so that if it sounds like a little confusing, maybe we're gonna look at this chart and then kind of sort things out. So here's the way I do it. So let me connect with this idea. Here's m swapping of the top row. Now here, let's think about this transpose, because this one connects the transpose. So I transpose this one. So this bottom row becomes the top row, and top row becomes the bottom row. All right. Now it's time to think about the connection between these two things, right? So here, transpose is not confusing, and that's the whole point of it. M swapping is kind of confusing. So in the middle of the way, this transposing is even confusing us. But transpose itself is not that confusing. That's the whole idea for breaking this one into these two pieces like this. So sigmas are swapping there into 1 through n to get here. Alright, so if you transpose to go there, and that's the tau 1 up to tau n is here. That's how the sigma is swapped around so that we get it down there. Think about the connection between these two. So to get here to there, to get the top rows, sigma is rearranged. Now in here, sigma is in the bottom. To go from here to there, it's exactly how the sigma is rearranged. That's the bottom row. So if you do exactly m swapping here, from here to there, then it's going to take this 1 through n exactly tau to n, because that's what we did here with the top row. That must be happening exactly the same way the bottom row, because transpose is easy to understand what happened to that terms. Again, top row rearranged, and here because we transposed, the bottom row is rearranged. Whatever that tagged with those bottom rows must be the same thing. That's why we have this tau 1 and tau 2 and tau n. Okay? Again, bottom row rearranged, top row rearranged. Along with that, what happened to this 1 through n is rearranged to tau 1 through tau n. That must be the same to the top row here, the 1 through n rearranged to tau 1 through tau n, as sigma 1 is rearranged to 1 through n. So at this point, it's clear that it takes m swapping to get to there, because all we're doing is rearranging the bottom row instead of top row after we transpose. So it takes exactly m swapping, right? So to some of you, it's quite easy and clear, but if you think about rearranging these product of scalars, and it's kind of obvious, but it's always fun to put into the so-called commutative diagram. And there are cases a lot more confusing, but sometimes this commutative diagram is presented here. Things are sorted out, and what part is trivial and what part is non-trivial. It's kind of well separated and nicely presented. So commutative diagram is always a powerful way of presenting order of operation problem. So last bit is, you have to pay attention to last bit as well. So we have this one, rearrange this thing so that it looks like that's the second indices are all lined up 1 through n. So here 1 through n, here the second indices, right? All re-swapped it. And then first indices are tau 1 through tau n. Okay? So in that, sign didn't change, it's just rearranged this scalar, product of scalars, into a different thing. So there's no sign change. Now you separate that first entries after you line up like this, first indices. Then think about rearranging this one to 1 through n. That's exactly this inverse map. If it takes m swap to get this 1 through n to here, you just do the exact each m swap in the opposite way. That's going to get you from tau 1 through tau n to exactly 1 through n. So that's inverse of this one. That's exactly taking m swapping in a reverse way. Therefore, the sign is the same. And that concludes the proof. And from there, we have the statement. Okay? If we have a matrix with aij determinant, determinant of aij matrix with n by n sides, then its transpose is going to be aji, and then if you write down the indices and carefully do the sigma notation, you can easily see that you're going to be dealing with that type of thing. If the sign of these things is the same, then you can easily conclude that determinant of A is equal to the determinant of the transpose of a matrix. Okay, so this is an important property in a statement, but what is more important is the theorem, which is shown here. This is also a very important statement. Okay.